Dear audience, with the help of the following few slides, I will try to provide an overview of the information security topics of SOA, Service-Oriented Architecture. SOA, besides promising unprecedented flexibility for the business, poses a number of new security issues, and without solving these, the flexibility can easily be reversed. Besides the business advantages, it can cause an equal number of disadvantages. However, you don't need to be afraid. The base principles haven't changed, and the solution modalities are available. It is important to handle the issue, but it shouldn't be over-dimensioned, i.e., information security should be viewed as a tool to achieve business goals in a broader sense. In this regard, SOA and information security walk hand in hand. I have divided the presentation into three main parts. First, we will review the components of SOA, mainly from the point of view of what must and what can be protected in a SOA architecture. In the second part, we will review certain issues of implementing business processes. The presentation is closed by a synthesis in which we put together a sort of SOA security model based on the previous learnings. Let's have a look at the components of SOA right now. Elements to be protected. Typically, the following components should be protected in a service-oriented architecture. Services and applications themselves. Applications, because not everything is SOA. There is a considerable number remaining. Communication between these, which is typically message-based, according to the principle of loose coupling. Business processes and their management. Possibly individual service components, databases, legacy systems, etc. SOA components, such as the ESB, Enterprise Service Bus itself. Users, or rather the other parts of the architecture should be protected from the users. Different hardware and other resources, communication infrastructure, electricity and water supply, etc. All these elements to be protected are called principles in the specialty literature. Let's check those that are most important from the SOA point of view. So what does the SOA architecture consist of? Obviously, there are services in there, since it has been named after those. Multiple definitions can be found in the specialty literature. I myself like to use the following, or I could put it this way, the following picture has been formed in me. The service is an independent piece of software that has a meaningful business function and a standard interface. This definition is suspiciously short, so it might be incomplete, but it captures the essence. The goal of SOA is to comply with the flexibility requirements of the business. Its tool is the reusability, which can be achieved by creating standard interfaces. The other important properties like loose coupling can be deducted from the definition. A piece of software that is meaningful from a business point of view can be of many types, of course, even dividable into further individual parts, or rather built from parts. These are composite, complex services that are created by connecting other services. This is the vertical complexity, where we can distinguish different levels of granularity in the architecture. We have horizontal complexity, when a service performs its activity spanning multiple physical systems through the cooperation of components on multiple platforms. For example, how would a service be that extracts part of its data from an application running on AS400 and another part from a Lotus Notes database? Obviously, this could be implemented vertically by bundling a service built around an AS400 function and one around a nodes-based function. But if we wouldn't use these services elsewhere, i.e. we wouldn't have reusability, then it isn't worth creating individual services out of them. Horizontal integration is better. The architecture is further complicated if we take the time dimension. In live architecture, new versions of the services are created and old ones are retired. This way, a complex fabric of services is formed where several variants of a certain type of service may operate simultaneously in order to fulfill various dependencies. A simple example is presented in the figure. Service A utilizes services X and Y. Namely, version 1.4 utilizes version 2.2 of X, and version 1.5 utilizes version 2.4 of X. Both rely on version 1.1 of Y. One could say, let's retire the old version of A, but we cannot do this without thinking, because version 3.1 of B utilizes it. Why did I tell all this? The presentation is not about services in general, but about the security issues of the architecture. But in order to face these, we need to explore the basic components and the structure of relations between them. And let me illustrate with a quotation how important the latter is. Relations are of key importance for a functioning architecture, as the great Hungarian architect István Örkény wrote in his short story, The Meaning of Life. If we lace up a lot of cherry pepper on a string, we get a pepper wreath. If we don't lace them up, we get no wreath out of them. But we have the same amount of pepper, the same red, the same strength, but no wreath. Does the string make it alone? No, it doesn't. That string, as we know, is a marginal, third-rate thing. So what then? Who thinks about that and takes care of his thoughts to not roam helter-skelter, but to head the right direction, that one can find some great truth. The semiconductor industry is able to produce for a long time now memory modules in which the count of storage elements is comparable with the count of the neurons forming the human brain. That is the order of magnitude of 10 billions. I think the companies of several honored spectators have servers with considerably more memory than 10 gigabytes. But nobody noticed that these machines would do thinking. Moreover, usually the contrary comes out. The answer to all the riddles is obviously the exaggerated simplicity of relations between memory cells. But let's get back to the security issues of SOA. From this point of view, the essence is that the services change in time and complex relations are formed between them. According to the SOA best practice, the number of services in a service-oriented architecture is roughly half an order of magnitude higher than the number of applications in the traditional architecture. At the same time, this means, since the system relations depend on the square of the number of base components, if we take into consideration point-to-point relations, that the number of connections is one order of magnitude higher than previously, although it wasn't low back then either, despite the enterprise application integration endeavors. The processes appeared among the components of SOA. Let's have a somewhat more detailed look at their properties. An important element of the SOA way of thinking is that it's process-based. The planning, modeling, management and measurement of processes, a little more precisely of business processes, create the transparency that leads to the identification, creation and efficient reuse of services. The processes quote-unquote utilize the services. The services provide individual process steps. In the relation of the two components, we find again the same type of complexity that we have experienced at the analysis of connections between different versions of services. Processes can run, although they shouldn't, in more than two versions that can use different versions of the same service. If we flip back to the earlier figure, we can consider A and B as processes, X and Y as services, and the explanation will still be valid. Processes, just as services, can be elementary and complex. An elementary process can be atomic as well, i.e., it cannot be interrupted during runtime. Complex processes can be shorter running or longer running. This is partly a question of feeling. To think through your whole life takes in regular cases hours or even days. But in certain cases this can happen in the 2 seconds between the 5th floor and the ground floor. From a business point of view, we can consider as long processes those that we cannot simply annul. For example, because in the meantime the daily closing has taken place, the item has already been booked, the client has taken the cash, the Giro has accepted the order. In such cases, if a runtime error occurs, a revocation, correction, or compensation process needs to be started. How do users get in contact with processes, and who are the users at all? As we discussed earlier, the users of services are mostly the processes. It is not typical that the agent at her workstation directly calls a service. Looking backwards, the services can be users or members of processes, but in a normal business process, the users are typically human players, employees of the company, partners, for example suppliers, and the clients. In a simplified way, the communication chain is built as follows. The user communicates with the process manager, usually through a thin web interface, for example a portal. The process manager calls different services that may access certain resources, possibly through other services. These resources can be either databases or traditional so-called legacy applications, but also hardware components, for example exchange rate displays, customer orientation systems, or automated teller machines. It is essential here that the traditional resources and the users do not come in direct contact anymore, i.e., agent Edina Kish doesn't log into the accounting system, but the portal interface authenticates her, and not a flesh and blood user will log into the accounting system, but the appropriate service will send a request to it. Naturally, the opposite direction of communication exists as well. Answers usually travel the same path backwards. After so much introduction, we can now proceed to the security issues of the SOA architecture. Let's review again the elements to be protected in SOA. We can see that there are many types of them, and as we discussed earlier, there's also many of them. At a mid-sized enterprise with the evolution of SOA, there can be approximately 600 services, 200 applications, around 200 servers, around 2,000 users, 100 processes as an order of magnitude. So we can quickly reach the figure of 3,000. If we allow at least theoretically each component to interact with each of the others, then the number of possible interactions move close to 10 million. Even if the situation is not that complex in reality, we cannot call it simple at all. Let's see how we can equip the interactions with safety features. How can we protect these components? Basically in two ways. Externally, i.e. using infrastructure components outside the components themselves, and internally, i.e. using methods built into the components as part of the business logic. One could imagine a solution that is built into the components, i.e. internal, but is not part of the business logic. This would be a paradox, because security is necessary to achieve business goals in a broader sense. So if we build it into the given component, then inevitably it becomes part of the business logic. One example of the external protection is the protection of communication channels, for example MQ channels, through SSL encryption. Through this, we protect the inviolability of data. We prevent unauthorized people from accessing and modifying those. Another example is the protection of hardware by isolation. We place them into machine rooms where access is strictly regulated, again to protect inviolability. With duplicated resources, spare servers in spare machine rooms, clusters, mirroring, duplicate backups, we raise the accessibility and undeniability of data to a higher level. These methods are well known, and since they don't influence the internal logic of the services themselves, they aren't even SOA specific. Authentication and authorization are more interesting issues. The authentication, i.e. the identification of the participant, is an external and an internal protection in a certain sense. It can be internal only as well if we build it into each resource, i.e. practically we have to log into each application separately. In the present state of scientific knowledge, this is not needed anymore. Moreover, authentication can be outsourced as a SOA service and centralized for the entire architecture. The first stage of this is single sign-on, and the peak can be the real SOA, where the user logs into a portal interface, that one authenticates her, and the further process management and service calls don't need to bother with this anymore. The authorization cannot be made completely independent from the internal functioning, since that determines the actual environment or context in which the permission needs to be evaluated there and then. Let's focus on this in the following. Let's see what SOA requires and what it offers in permission handling. If a participant, that or who can be a person or a program, would like to utilize the capabilities of a resource, a service, an application, data, or some real thing, then it gets in contact with it. The figure illustrates the security points of this connection. The participant first faces an enforcement point. She cannot turn directly to the resource. If it didn't happen earlier, she needs to identify, authenticate herself, whether she is she. Then it needs to be decided whether the given participant can execute that interaction under the given rules, policies, contracts. For example, it is possible to lock up deposits without special authorization up to a certain limit value, based on the normal deposit lockup service and possibly other attributes, for example, whether it is during working hours or is there a compensation process running. This is the authorization that needs to be performed for each interaction. Applications have been performing such authorization previously. Why is this different in SOA? Primarily because a key attribute of the services is reusability. If there is reusability, there is SOA. If there is no reusability, there is no SOA. Multiple clients having different security rules connect to the services. Therefore, these rules cannot be abstracted from the environment and built into the interior of the services. In SOA, Adinokish doesn't execute a deposit lockup, but in a certain phase of the customer contact process, she launches a sub-process in a certain phase of which the process manager calls the lockup operation of the deposit handling service. I mentioned earlier the compensation processes on purpose. There the situation is even more complex. It can easily happen that the agent has launched the process based on the customer's request, and at a certain point of it, she performed a lockup for a large amount that needed special authorization. But an error occurred in the later phase of the process. Say the customer didn't present the required documents. Now the compensation process that has been launched by the agent or automatically, but is running under the agent's name, needs to be able to unlock the large value deposit, even if the agent herself otherwise would not personally have permission for this as an individual step. Briefly, Adinakish in SOA will not have permission to the deposit lockup menu item of Capiti equation. Instead, she can contribute to certain steps of the deposit lockup business process. On the other hand, the option behind the deposit lockup menu item of Capiti equation doesn't need to analyze who is the person by name who wants to perform the operation. Instead, it always needs to allow the caller service to perform it, since this question has been already decided earlier. Solution: the permission handling needs to be taken out of the applications or services, i.e., the authorization needs to be externalized. It is very important to observe that this externalization is not a constraint, not a restriction. It is rather a possibility and an extension. Using it, we can achieve that we don't need to deal with permission handling of silo applications. Instead, we define rules that are necessary and sufficient for execution by regarding the process steps related from a business point of view in a unified way. If we have a closer look at the role of the decision point in making the interaction more secure, we can see that it has a function that is meaningful from a business point of view. Definitely a standard interface can be created for it, and all permission handling functions can be its client. According to this, it has all the criteria listed in the definition of a service, and certainly it will be reused several times, so let's make a SOA service out of it. It's been made. We call these services rule engines. A concrete manifestation of this service class, as you've probably already guessed, is TCPS for SOA. Further on, we will be able, with the interpretation of my colleagues, to dive into details, to get acquainted with its structure and usage, and to see where else a rule engine can be applied other than authorization. But before that, let's review using a slide the steps of creating an externalized permission handling. In order for the permission handling to be externalizable, we have to think about it already when collecting business requirements. To successfully execute this, appropriate roles have to be created in the organization so that this planning doesn't happen in an ad hoc manner, but the knowledge acquired through projects is cumulated in the members of the development process. The business area and the business analysts have to assess what roles are related to and what business rules should be applied to the usage of the business functionality to be developed. Since the latter are extracted into a separate service, we don't need to deal with it when developing the main functionality. It is enough to finalize the rules before go live. What needs to be decided during planning, the next step of the development process, is the following. What are the components to be protected, and where are the enforcement and decision points that need to be built into the functionality? By functionality, one can mean an application, a process management, or a service in the interaction with components to be protected. The context to be transferred with the question and other attributes to be evaluated need to be defined here, respectively from where, possibly from which external systems those need to be retrieved. The developer's task is easy with the externalized permission handling. In the actual functionality, the connection to the decision points needs to be developed, i.e., the permission questions need to be sent to the rule engine. It is very important to mention that the roles should be handled on process level rather than on application or service level, i.e., one shouldn't build in roles into a service or application because their scope is rarely the given application. Almost always, the entire business process or even the entire company organization. The applications, services need to ask only elementary permission questions. The rule engine will interpret the roles. The task of testing is twofold. On the one hand, we need to verify during unit test that the system indeed asks the questions to be asked at decision points, and whether it continues based on the received go, no-go answer. Respectively, during user tests, it needs to be verified whether the evaluation happens according to the predefined business rules. The task for operations is to provide adequate resources for the externalized permission handling in order for it to be able to serve the entire architecture with short enough response times. Another task is the maintenance, upgrade of rules, which means in ideal cases the upload of new rules verified in the test system into the production system. Naturally, before the change process reaches this point, it goes through again iteratively practically through the entire development cycle outlined above. The job of security experts is to follow through the entire development cycle from the assessment of business requirements to operations. They can operate most efficiently if they not only supervise the development process but participate in planning, namely not only on the level of the given project, but keeping in mind the security issues of the entire architecture. The owner of this task can be the so-called security enterprise architect. Thank you for your particular attention. You are welcome if you may have questions, additions, comments. Please write to the address mesavos.gyula@tlogic.hu.